and initialize arrays. We'll look at how we access them with subscripts, and we'll also take a look at multidimensional arrays. We'll wrap it up with a short discussion on files. We'll look at some of the library functions we can use to read and write text files in C. So arrays let us store a ordered set of data in memory. So instead of defining a single int variable, we can define an array variable that holds a multiplicity of integers. So some examples might be as follows. I could define a array called values to hold 100 integer values, or I could use a different type. So I've got a car name that will hold 25 character values. We can also provide initializers for our arrays. So for example, my int values with 4 elements, I could assign it a initializer by including a list of integers, comma delimited integers, in between a left and right curly brace. Similarly, I could define an array of characters along with an initializer. So here I have the word hello spelled out as character literals, again in between the curly braces. Now, one of the things I can do when I'm using these initializers in C is I can leave off the size specifiers when I define the array. So in this next example, I've got an array called name, and you'll notice that I left the size out, but I set it equal to the characters FRED. And so basically, when the compiler sees this, it's going to allocate an array of 4 characters. Another thing we can do with these initializers is as follows. So look at the example int big array. Again, I've left off the size specifier, so it's going to create the array based on the size. But what I can also do is I can set individual elements within that array to specific values. So I'm putting the subscripts in square braces. So inside the curly brace initializer, you see that the 0th element is being set to 1. The the 1 element, or subscript 1, is getting a 10. And then I have a 999. So element 999 is equal to 0. And so what the compiler does is it looks at that initializer and it takes the largest index that appears, and that will be the size of the array. So in this case, 999 is the largest index. But one of the things I haven't mentioned yet is that in C, all the arrays are 0 base. So if the largest number is 999, that means that the array is going to have size 1000. So it's going to run from the indices 0 up to 999. Now you might be wondering what happens to the other 997 elements in this array. Well, nothing. They're actually left undefined in this case. So only the ones that we specifically listed in the initializer are defined. The rest of them are going to be uninitialized. So we can't rely on what they're going to be. They'll be whatever they are. And so just keep that in mind if you use this particular technique. Now we can access elements in an array using these subscripts. And once again, you should note that these arrays are always 0 based in C. So if I have an array called values, int values, and I set it to be 100, it will have 100 elements, 100 integer elements, and the indices are going to range from 0 to 99. Now, in the first example, I'm showing I can use this a subscripted, an individual element in the array in any location where I'd use any normal variable of that type. So I've got the statement values sub 23, and that's normally how we'll read these things. Values sub 23 equals 911. What I'm doing is I'm assigning the integer value 911 to the values sub 23 location in the array. I can also use the array element on the right side of the statement. So in the next one, I have an integer j being assigned the value of values sub 23. In the last example, I've got something else. I've got values sub j is going to equal 912. And now if we assume these statements were consecutive, we see that values sub j is actually going to be values sub 911, but the array only goes to 99. So what happens when I use an index like this or a subscript that is actually out of range? It's beyond what the array has been signed for. Well, the C compiler is not going to check this type of condition for us. If this happens in our running program, one of two things might happen. If the address was actually invalid, the program will crash. There'll be a memory fault and it will crash. But in other situations, if it was indeed valid, in other words, that address does map to my address space, it might just use garbage data, whatever is at that location. Now, neither of those situations are good, and both of them are going to result in have unintended consequences with regard to our program. So you're always going to want to make sure when you use arrays that those indices are actually in range and correct. We also can have multi-dimensional arrays in C. And here I've got an example, values, and I've defined it to be a 2 by 2 array. And I can have arbitrary dimensions. This one just shows 2 dimensions, but I could in fact have as many dimensions as I want. And I can also use initializers with these multi-dimensional arrays. So I have another example here, int values 2, 2, the same multi-dimensional array, 2-dimensional array in this case. And notice how we use the braces to set off the different rows. So in this case, the first row of the array is going to have a 0, 1, and the second row of the array is going to have a 1, 0. Now if we leave those internal braces off, the compiler is still going to fill the array out in row ordering. So the initializer, the third example here, is going to do exactly the same thing as the second example. Now, we access the elements in a multi-dimensional array very similar to what we do with a linear single-dimensional array. So here is an example where I'm accessing values, and it's going to be the row with index 2 in the column with index 3. And once again, these are 0-based. I can also assign values in a multi-dimensional array using the same type of indexing. So here I've got values sub 0, 2, so row 0, column 2 gets the value 1000. All right, so we'll look at some examples of code using arrays in a moment, but before we do that, let's take a quick look at some of the file I/O routines we have in the standard C library. So before we can read or write to a file in C, we need to first open the file, and we can do that with the fopen command. When we're finished using a file in C, we're going to close that file, and we'll use the call fclose to do that. Now, there are obviously parameters that we use with these calls that I'm not talking about at this point, but when we see some code examples, we'll actually see what those are. And you should know that you can also read more about these functions on your Linux or Unix or Unix-like systems such as Linux by simply issuing a man command. So on your bash shell prompt, if you just say man space fopen, you'll have all the detailed documentation for fopen, and you can do that with any of these library calls that we're discussing. So when we work with these file I/O functions, things happen, bad things happen. We have error situations that come up. And there's different ways the C language lets us get at this information. So there's a variable called errno, E-R-R-N-O, which is a globally defined external integer, and it's set to the last error code. So when we call one of these routines, if something went wrong, we can consult this errno value and find out what the error number was, and each of these error numbers has a definition. In order to access that variable, we need to have a pound include errno.h at the top of our source file. Now there's another way we can get at this information as well. We can call the function ferror, and it will actually return the error number for the last file operation that failed. We can also use a function called perror, which actually prints out a textual description of that error. So instead of having just the number, which may or may not make sense to us, we can print out the actual text describing that error message. So these are handy functions to use when we're trying to debug our program. So we have a variety of options for reading from text files in C. We have a library call called fscanf, which is analogous to the scanf that we've already looked at for reading from standard input. So fscanf works just like scanf. The only difference is the input is now going to come from a file, an open file, instead of just the standard input. We also have fgetc, which lets us read from a text file one character at a time. So this is very similar to the getchar we saw previously to read from standard input. We also have fgets, which lets us read a line at a time from a text file. So we can read an entire line of text with one call to fgets. Similarly, for writing, we have an fprintf, which is analogous to the printf command that we've already seen. Only now, instead of standard output, when we use fprintf, the formatted output ends up in the file, whatever file that is open that we pass to the fprintf. We also have an fputc, which is analogous to the putchar that we've already seen. It lets us write to a text file one character at a time. And finally, we have an fputs, which lets us write to a text file one line at a time. So just to pull that all together in some simple examples, I've got some code fragments here. In this example, the very first statement you'll see is a fopen. And this statement opens the file for writing, and you'll see that I've got two parameters. I've got the name of the file, so that's a string, the first thing, and the second argument is a permissions indicator. It basically tells the mode of the file that we're going to open. In this case, we're going to write to it, and it's going to truncate if this file already exists. Now, the value that is returned from this is actually what we call a pointer. Now, we haven't talked about pointers yet, and we will shortly in a future lesson. But for now, just take this on faith. It's a pointer, and the only thing you need to know at this point is that pointer, in this case it's called fout, and we know it's a pointer by the little asterisk before the variable name in the declaration. But that fout refers to that open file if this command is successful. It's going to get a non-null, which means it's a non-zero value, and it will then be referenceable in the future when we use some of these other calls. So the if statement right after the fopen here is simply checking to see if indeed this file has opened successfully. If it hasn't, it's going to call perror, which prints out the message we gave it, plus whatever message relates to the error number that was returned from that fopen. And it could be something like the file doesn't exist, or we didn't have permissions to write to that file, and so forth. Once we've got the file open, we're going to write to it. And we're using the fprintf call to do that. And the fprintf call, there are two of them. In one of them we're writing, this is going to be some comma delimited values that we're writing out to a text file. So the first printf prints out the words time, latitude, longitude. And then we're iterating through some data, and we're printing out three values, an integer followed by two floating point numbers, to this file. And we're doing some calculations to calculate these numbers. And the last thing we do is we close the file out when we're done updating it. Reading works very similarly. So here we have an fopen, and you'll notice now that my mode is just a single R. So I'm opening this file for reading. Once again, I also have an if statement checking to see if I got a non-null file pointer back. In this case, the file pointer is being stored in a variable called fin, or fin, F-I-N. And if it opens successfully, we move on and we actually read from this data using an fscanf. Now this is actually the analog of the previous example. So this code here is reading the file that we wrote in the previous code fragment that we showed you. So we're going to read in our loop until we hit a end of file. We have a single read on the top because we're assuming there's some headers in there that we want to skip. And we simply print out all the data that we're reading to standard output using a printf statement. The last thing we do is we close out the file by calling fclose and passing that file pointer. Alright, let's take a look at some examples of code that uses arrays as well as these file input-output function calls. Let's take a look at a simple program that uses arrays. I'm going to write a program that sorts a simple list of integers that the user enters from the terminal window. So let's go ahead and include the standard I/O header because we'll be doing some I/O. And before I define my array, I'm going to assume that there's a max number of integers that my program will read. And I'm going to assume it will read 10 integers max. So what I'm going to do is put a preprocessor directive up here. I'm going to put a #define, and I'm going to put the symbol max in all caps in a 10. Now, what this does is the preprocessor, when it sees this defined, will replace every occurrence of the string max in all caps in my program with the value 10. So now when I define my array, I can go as follows. I can say int, and I'll call my array data, and I want max elements. So this will give me 10 elements, and they will be indexed from 0 to 9. Now I'm going to do a sort, so I'm going to need some loop variables here. So I'll define a few more integers, and the first thing we're going to do is read in the data, and we'll just read it from standard input at this point. So I'll go into a loop and I'll say from I equals 0 so we'll read in 10 integers. There we go. So there's a loop that reads 10 integers from standard input. Hopefully that looks familiar to you by now. And once I've got the data read in, I'd like to just print it out to confirm that's what I got. So I will say print f, and for each element in the array, I'll simply print it out. Okay, let's just test our program so far and see if it's working. Okay, so it looks like it's read in 10 numbers and then was able to print them out. So far so good. Now let's go ahead and write the sort algorithm. Now we're just going to use a really simple, straightforward sort algorithm here. So we'll just have some nested for loops. So if the ith element is greater than the jth element, we're going to go ahead and swap those values. So the smaller items are going to get placed before the larger ones. So that is our simple sort. And now that we've sorted it, let's print out the values. offset this a little bit. Okay, let's see if this works. Sure enough, we've basically sorted the the list of integers that we've read in. Okay, now let's go ahead and do some file I/O with this program. So we'll take the same program, the sort program that we just wrote, and instead of reading this data from standard input, let's go ahead and read it from a file called input.txt. So I'm going to need a file pointer variable in order to open a file. So I'll go ahead and define that as a variable called fp. And when I read in the data, before I read it, I'm going to try to open the file. So let's go ahead and do it open. And we'll call the file input.txt. And we will go ahead and open the file for reading. And at this point, if I have a file, so if the file pointer is null, then we're going to just print an error message out and just exit. Now, if the file is open, at this point, I'm going to read from the file instead of standard input. So I won't need this prompt anymore. So we'll comment that out. And I'll change this to an fscanf. And I'll go ahead and add the file pointer. And that should be all I need to do to read this file. But remember, when we read a file, or when we open a file, we always close it as well. So let's go ahead here and close the file since we're done with it at this point. We now have the data loaded into our array in memory. Let's just check our work so far. Okay, so it's working exactly like we thought. There was no file input.txt, so it's doing exactly what it should do. So let's go ahead and now create the file. Okay, so there's the input file, and let's try simple sort one more time. Oh, still couldn't open it. Oh, index. I have the file name wrong, so it's actually input.txt. That should work. Okay, so sure enough, now we're able to actually run the same program, do the sort, but now we're getting the data from an input file. And let's do one more modification. Let's actually write this data, the final data, out to a file called output.txt. So we need to do a similar thing here. We need to open a file called output.txt, and we're going to open this file for writing and have it truncate. If the file is not there, it'll just open an empty file. If the file is there, if it already exists, it will truncate it and then write the new data to it. So if the file pointer was null, once again, we need to check that condition. So if it was null, we want to say something like and if we succeeded, let's go ahead and turn here. And if we succeeded, we want to go ahead and write the data. So we'll change this to an fprintf and put the file pointer here. And we have one more printf right here. We'll change that to a printf and put the file pointer here. And remember, the last thing we do when we're done writing this file, we're going to need to close it. So let's go ahead and try this. Okay, so it said you entered the following, so that was still going to standard output. So if we did everything right here, we should have a file called output.txt with all those integers sorted. And sure enough, we succeeded. So now we've seen how to use arrays in a simple C program that sorted some integers, and then we went ahead and added some file I/O functions here so we could read and write that data from files instead of standard input and output.